Hello students, welcome to this channel. In this session we are going to learn about relative acidity of some organic compounds. So an acid is expected to release H plus ion in the solution, hydronium ion to be precise, and its conjugate base. So this species is known as conjugate base. Okay. And only if it releases a proton in the solution, I can call the substance as an acid, right? Now the strength of acid can be directly measured by the stability of this conjugate base, right? Greater the stability of this conjugate base, stronger the acid. So a strong acid will release a stable conjugate ion. So I can say strength of acid, right? Strength of acid can be directly correlated with the stability of the conjugate base. Stability of conjugate base. This is what we are going to discuss. The relative acidity of organic compounds can be understood by the relative stability of the conjugate base that is going to be generated after the release of proton. Now let us understand the relative stability of a conjugate base that is going to be produced in these species, okay, and so that we can able to find out what is the correct order of acidic strength of these compounds, correct? So here three compounds were given, right? A, B and C, right? A, B and C. Now after the release of this hydrogen, this species is going to be generated, right? Okay, and here also I'll get a negative charged, and after the release, this is the conjugate bases. These are all the conjugate bases that are going to be generated after the release of H plus ions, right? Now let me see the alpha carbon. Alpha carbon, I have CH2, which is a sp2 hybridized, and it is common in all these three cases. Whereas in the beta carbon, right, I have sp3 hybridized carbon in the first case, and I have sp2 hybridized carbon in the second case, and in the third case I have sp hybridized. Now the negative charge that is generated on oxygen should be decreased so as to increase the stability of that intermediate intermediate ion, right? So sp hybridized carbon is more electronegative. We all know that. So sp hybridized carbon will effectively withdraw electron density from in this direction, so that the negative charge generated on the oxygen in this conjugate base will be stabilized by drawing more electron cloud, and will be stabilized by the spreading of negative charge throughout the compound. So that's how compound C will be more stable than compound B, and which is more stable than compound A. So the acidity order will go in this direction. So C is more stable than B than A. It is all due to the sp hybrid, more electronegative carbon and its minus I effect. Okay, so simply saying minus I effect will increase the stability of species that carries negative charge. Now let us take the another case, right? Here in the first case I have benzene, and the second case I have toluene, and third case fluorine substituted toluene, right? Now what will be the conjugate base that will be generated after the release of H plus? Let us understand hypothetically. After the release of this hydrogen, this species is going to get this is the species that I am going to get, right? Phenyl anion, right? And after the release of H plus from this species, I am going to get CH2, that is phenyl anion, right? And here after the release of hydrogen, I am going to get this species, right? CH minus connected with the fluorine. Now let us understand the relative stability of these species. Okay, we know that a phenyl anion is the least stable because it is going to bring anti-aromatic character. The number of pi electrons is going to become 8, so which means it tends to become anti-aromatic. Anti-aromatic compounds are lesser in stability than aromatic compounds, so release of this hydrogen will be very, very difficult. So this is the least acidic one. Now let us come to the second case, B. Now this negative charge can be resonated, right? This negative charge can be resonated, and such resonance structures will bring stability also. But when we look at this third case, this negative charge will be drawn by the more electronegative atom fluorine. So this will draw electron cloud, okay, fluorine is minus I group, so it will reduce a portion of a negative charge due to minus I effect, and that's how it brings stability apart from stabilization due to resonance. So here resonance come minus I effect, both will be acting harmonically so as to bring more stability to this species. That's why compound C, the intermediate that is formed in the compound C will be more stable, and that's why that is more acidic. So the acidity order goes in this direction. C is more acidic than B, which is more acidic than A. Now let us see an interesting case. Here I have three compounds. The first one is a fluorine substituted toluene, second one is chlorine substituted toluene, and the third one is bromine substituted the toluene. Okay, so after the removal of hydrogen as H plus, these carbon ions are going to be generated respectively. So I'm going to consider this. So these are the intermediates that can be expected to be generated in the species. Okay, so now we need to find out the relative stability of these species. Okay, so we expect that a more electronegative atom will draw electron more effectively. So fluorine is the most electronegative one. So A compound, the intermediate produced from compound A will be more stable. So the acidity order should go like this: A is greater than B, which is greater than D. This is what it is expected. But to our surprise, compound B is more stable than C than A. This is what actual. Okay, let us understand the reason. Now there is a negative charge present on the carbon in the compound B, right? So here the negative charge is residing on 2p orbitals, right? And chlorine has a vacant 3d orbital, right? Vacant 3d orbitals. What happens? This 2p orbital, the negative charge on the 2p orbitals of carbon can be donated into the vacant 3d orbitals of chlorine, and this kind of donation is called as back donation or back bonding. Such back bonding will increase the stability of this species intermediate, I mean the carbon ion that is generated from the compound B. Okay, and of course there will be back bonding in the compound C also. The negative charge can also be donated into the vacant orbital of bromine, but it is going to be donated into the vacant orbitals of 4d. But because of the bigger size of bromine, the 4d orbitals will be larger, and the electrons from the 2p orbital cannot be effectively donated into the vacant orbitals of 4d. So that back donation is not as effective as in the case of compound B. Okay, so that is why compound B, the intermediate generated in the compound B will be more stable than the intermediate that is generated in the compound C, whereas no such vacant orbital is available with fluorine, and that's why just minus I effect operates, right? So that is why compound A is lesser in acidity, and this is the order. Now let us look at the fourth case. Okay, so here I have chlorine substituted toluene and dichloro or 2 chlorine atom substituted compound, and there is a methyl substitution at the para position in the compound C, right? Now again hypothetically we will consider that after the release of removal of this hydrogen, this species is going to be generated as a carbon ion, which is an intermediate, and here this hydrogen will be leaving, and this species is going to be generated in compound B, and of course in compound C this is the intermediate that is going to be generated. Now let us understand the relative stability of these three species, right? Now as we learned that in the previous case, this negative charge from the 2p orbital can be effectively donated into the vacant 3d orbitals of chlorine, and which brings stability, extra stability, back bonding, right? So we know that A is more stable, but in compound B the intermediate has 2 chlorine atoms, which means the back bonding can be done with both the chlorine atoms, which means it will bring some extra stability. The stability of B will be more than A. Okay, so B is more stable. But when we compare with this one, the third one, see I have a methyl group that is attached to the para position, and we know that methyl groups are plus I groups, right? So it will increase the electron density in the ring, and it will also have an impact on the increase in the electron density on carbon, right? So the negative charge density increases. So increase in negative charge density will actually decrease the stability of carbon ion, right? We have learned that an electron donating group will actually decreases acidity, right? Will decreases acidity, and that's why C is least stable, right? C is least stable, then comes A, and B is more stable. Okay, now let us understand the relative stability of these three species, which is very interesting, right? So we are going to compare the intermediate that is going to be generated in all these three species, and we are going to understand the the acidic strength based on their relative stability. Okay, so hypothetically I am going to consider that this hydrogen is going to be released as H plus, so that will bring a negative charge on this carbon in the compound A, and in compound B again this hydrogen is going to be removed and negative charge will be generated on this carbon, and of course the same thing will happen in the third compound also. So this carbon is going to gain negative charge, and in the first case we know that there is a vacant d orbital present in all chlorine atoms, right? Vacant 3d orbitals. Now the negative charge is there in the 2p orbital of carbon, which can be effectively donated into these vacant 3d orbitals of chlorine, and that is nothing but back bonding. So this back bonding will happen with all three chlorine atoms, and back bonding brings stability, dispersion of negative charge, right? So that's how species A that will be stabilized, right? Now let us understand what happens in compound B. The intermediate carbon ion, which is generated like this, will involve in resonance, because this is carbon present in the cyanide is sp hybridized. We all know this. So it will draw electron cloud towards it, and it goes in this direction, which will cause this negative charge to come here, and which will form a new bond between carbon and carbon, new pi bond, and the one of the pi bond will be shifted towards the nitrogen. So and this kind of intermediate will be formed, right? Carbon will get carbon nitrogen will get negative charge, double bond, and nitrogen is going to carry negative charge here, and this is how the same thing will happen with all these three cyanide groups, right? Now just like that, and this is a kind of resonance, right? Resonance will bring stability, we know that. Now resonance due to charge, the bond formation, this kind of resonance, this is called actual resonance, and here the resonance is due to back bonding, right? 2p 3d or p pi d pi kind of back bonding. This is also a kind of resonance, but this actual resonance is more stable than this p pi d pi back bonding kind of resonance, right? So surely B is more stable than A, and the same thing will happen with compound C also, but here one thing is different. This nitro group, this nitro group actually, so if I find out the real structure of or the complete structure of NO2 group, we can able to understand it clearly. So this is the structure of nitro group. What happens, this negative charge will come here, and a new double bond is about to form, which will repel the pi bond towards oxygen. So we will get a species like this, right? So carbon, nitrogen will have negative double bond, and there will be a coordinate covalent bond with oxygen, and here negative charge will be there, right? Now in the case B and case C, negative charges are produced on more electronegative atoms, whereas in case B the negative charge is generated on nitrogen, see, whereas in the case C the negative charge is generated on oxygen, right? We have two more NO2 groups, of course. So negative charge, more electronegative atom carries negative charge, is more stable, this very basic rule, we know that, right? So negative charge on oxygen is more stable than negative charge on nitrogen. That's why compound C is more stable than compound B, which is more stable than A. So that is also the relative stability of acidic order for these compounds. Okay, thank you guys, thank you for your patience. Please do subscribe my channel. Thank you. Happy learning.